So here is the first example in our review. I would like to compute the following limits. All right, so I would like to compute the following limits. As I said, our goal is to recall this idea in terms of example. Let me remind you how we came to the idea of the limit. We asked one very simple question. The question was, what is the best way to understand the behavior of the function when x is near a particular value a? Answer was very simple. The best way to understand the behavior of the function when x is near a can be understood by simply plugging x equal to a into the function itself. All right, and see what happens. Here is the first example. Let's say I would like to understand how my function 2x plus 3 over x squared plus 4 behaves when x is near to. Once again, this is how we are going to read it. We would like to understand the behavior of this function when x is near to. Remember, limit is a prediction only. Your function may or may not take that value at that exact input. All right. So we are kind of making a prediction. We realize that the best way to understand this behavior is to plug x equal to 2 into the function and see what happens with our function. Looks like I get 4 plus 3 in the top, 4 plus 4 in the bottom, and I end up getting 7 over 8. If you end up with a number, non-zero number, that non-zero number is the limit of the function. This is how I read that first statement and the ending result. When x is arbitrarily close to 2, my function is arbitrarily close to 7 over 8. All right, so again, this is a prediction only. When x is very close to 2, this function should be very close to 7 over 8. That's how we interpret this first statement and the ending result, right? Let's try one more illustration. Here is the second one. Let's say I would like to calculate limit x approaching to 2 of x squared minus x minus 2 divided by 2x plus 5. Once again, we kind of play the same game. To understand behavior of this function, when x is near 2, I would plug x equal to 2 into my function. At the moment you replace x by 2, you should stop writing the limit symbol. Remember, this means the limit has been applied on the function. We are computing the outcome. Looks like in the top I get 4 minus 4, in the bottom I get 4 plus 5. This is really 0 divided by 9. This can be viewed as 0 multiplied by 1 over 9. If you multiply any non-zero number with 0, the final result will be 0, right? So this is what you get. All right, so when x goes close to 2, this function goes close to 0. That's how we read this statement. Let's try another one. Here is one more illustration. Limit x approaching to 3. Let's say we have 2x plus 7 divided by x squared minus 9. Do the same thing. Plug x equal to 3 into the function and see what happens. I get, 2 times 3 plus 7 in the top, 3 squared minus 9 in the bottom. Top is 6 plus 7, bottom is 9 minus 9. We get 13 over 0. We know that division by 0 is illegal mathematical operation. This simply means that this limit does not exist. Let me mention here that when computing limit, these are the only 3 possible cases that we have. All right. If limit exists, it must be a non-zero number, or it must be 0, or it must be undefined. All right. Besides these three cases, we don't have any other case possible as an outcome of the limit process applied on the function. All right. Okay, so now it should be clear that this case represent non-zero output for the given function when x approaches to 2. This particular case refers to x-intercept for your function. All right, when x is near 2, this function experiences x-intercept. This particular case, the one in the denominator, the one where we get 0 in the denominator, it represents vertical asymptote, right? This function experiences a vertical asymptote when x is near 3. If you remember, there was one more very particular situation that arises when we plug x equal to a into the function. It may happen that when you plug x equal to a into your function, you may get 0 in the top as well as 0 in the bottom. What should we do then? Well, if you recall, that particular form is called indeterminate form of the limit. For example, let's say I give you this function. Let's say we would like to understand the behavior of this function when x is near 2. I would try to apply the same strategy. I would plug x equal to 2 into my function. I get 2 square minus 2 minus 2 in the top, 2 square minus 4 in the bottom. The top is 4 minus 4, bottom is 4 minus 4. We get 0 in the top, 0 in the bottom. This particular form is called indeterminate form. All right. Remember, if we have 0 in the top with non-zero bottom, limit is 0. If we have non-zero top with 0 in the bottom, limit does not exist. But if we have 0 in the top and 0 in the bottom, we don't know what we are going to get if we attempt to divide 0 by 0. All right. And that is the reason why it's called indeterminate form. This direct substitution doesn't let us determine what the limit would be. All right. Recall, what were we doing to handle indeterminate form? Well, we had three traditional techniques: rationalization, factorization, algebraic simplification. Remember, factorization is recommended for polynomials. Rationalization is recommended for expression involving radicals. Algebraic simplification is recommended for numerator and denominator given in form of rational expressions. All right. So looks like top of this expression is a polynomial. Bottom of this expression is a polynomial. Factorization is a trick to use. Let's use the factorization to see what we get here. I have limit x approaching to 2. I am looking for the factors of -2 whose sum is -1. The factors of -2 whose sum is -1 are going to be -2 and +1. Convince yourself that we can write down this factorization directly because this polynomial is monic, right? Denominator can be seen as a difference of two squares, x square minus 2 square. Factorize it using a square minus b square formula. Factorization would be a minus b, a plus b. What does factorization do? Factorization gave us an opportunity to see the problematic portion as a factor. When I say problematic portion, I really mean the portion that creates 0 in the top and 0 in the bottom when you plug x equal to 2. When I plug x equal to 2, that's the part that creates 0 in the top. That's the part that creates 0 in the bottom. Since it's visible as a factor, I can cross it out. So what I did is I basically got rid of 0 from the top and the bottom of my function. And once that 0 is gone, we can apply the limit. All right, we can apply the idea. Plug x equal to 2 into your function. You get 2 plus 1 in the top, 2 plus 2 in the bottom. Be sure when you replace x by 2, you should stop writing the limit symbol, because this really means the limit has been applied on the function and that's the outcome, right? So again, this is one of the old technique that we have used to compute, to handle indeterminate form. If you remember, we talked about L'Hopital's rule. This is the fastest way to handle indeterminate form. Let's recall that method. Let's apply it for this particular example. Let's say I have limit x approaching to 2 of x square minus x minus 2 divided by x square minus 4. All right, once again, I would plug x equal to 2 into my function. It is clear that this is indeed 0 over 0 form. Right? Plugging x equal to 2 gives me 0 in the top, 0 in the bottom. Right? Now, instead of using traditional technique, factorization technique, I would like to use L'Hopital's rule to get rid of 0 from the top and the bottom. All right? Let's do that. By L'Hopital's rule, we can say the following. You need to take the derivative of the top expression, take the derivative of the bottom expression, and apply the same limit on the ratio of these two derivatives. Once again, pretty simple deal. All you have to do is differentiate the top polynomial, differentiate the bottom polynomial, take the ratio, apply the same limit. What we are saying is that this process will eliminate bad factor from the top and the bottom. Good news is we don't have to worry about factorization of the polynomial. Understand that factorization of the top and the bottom polynomial could be complicated if the polynomials are of higher degrees. All right, it's much more tricky to compute factorization. If I replace top and the bottom polynomial by third and fourth degree polynomials, and if that involves indeterminate form of the limit, factorizing those polynomials requires some time, right? Calculating derivative of those polynomials are super duper simple, because all we need to use is the power rule, right? Differentiating top, differentiating bottom is like less than 15-second work for us. All right. So we are saying that this L'Hopital's rule really eliminated one bad 0 from the top and the bottom. I can apply the limit now. Replace x by 2 in the top and the bottom. I get 4 minus 1 in the top, 4 in the bottom. Looks like we end up getting exactly the same result. As I said, the reason why I keep these two methods side by side is to show you that how L'Hopital's rule can be used over traditional technique, right? So traditional techniques, yes, they are helpful in some particular set of problems. However, for those same particular set of problems, L'Hopital's rule might, give you answers faster, right? Okay, now let's try to see a couple of more examples to demonstrate the real use of L'Hopital's rule. It is possible to create rational function involving exponential and logarithmic function where the traditional techniques don't work. So here is example number 5 and 6. Let's say I would like to calculate limit x approaching to infinity of e to the x plus 7 divided by x square. All right, and let's say we would like to compute this limit as well. Limit x approaching to infinity of natural log of x square plus 7 divided by 2x. We are again going to take the same route. If you want to understand the behavior of this function when x is near infinity, plug x equal to infinity into this function. Look, I get e to the power infinity plus 7 over infinity square. Remember, infinity is a symbol only, and this is a tedious symbol. Why is it a tedious symbol? Because doesn't matter what you add to infinity, you still get infinity. Doesn't matter how big quantity you subtract from infinity, you still get infinity. If you subtract, let's say, 100 millions from infinity, you still get infinity back, right? So this is a tedious symbol. You square infinity, you multiply infinity with infinity, you still get infinity back, right? And that's why I say this is a tedious symbol. E is 2.71. Any number bigger than 1, its infinity power leads to infinity, right? So this is infinity plus 7. The top will be infinity, bottom will be infinity. This is indeed an indeterminate form of the limit, right? Meaning I can use L'Hopital's rule here. Understand that the traditional techniques are not going to work. This is not a polynomial, so I cannot use factorization, right? I was able to use factorization here because top and the bottom, they both were nice polynomials. This is not a polynomial, so I can't use, factorization. Can I use rationalization? Answer is no. There is no radical expression in the top or the bottom, right? So I can't use rationalization either. So that leaves me with one final choice. Can I use algebraic simplification? In the top, I don't see rational expression. In the bottom, I don't see rational expression. I can't use algebra to simplify rational expression to make the problematic portion visible as a factor. All right. I only have one option left, and that's L'Hopital's rule, the fastest way to compute the limit. Let's use it by L'Hopital's rule. I'm going to differentiate the top function. Derivative of e to the x is e to the x. Derivative of 7 is 0. In the bottom, I get derivative of x squared, that is 2x, and I apply the same limit. All right. Again, when you apply the L'Hopital rule, it should be clear that when you take the ratio of the derivatives of the top and the bottom, you eliminate one bad copy of infinity from the top, one bad copy of infinity from the bottom. All right. Once that is done, we again attempt to plug x equal to infinity. I get e to the infinity in the top, 2 times infinity in the bottom. Looks like this is still infinity over infinity form. Meaning direct substitution did not help. I can use L'Hopital's rule one more time to get rid of one more copy of infinity from the top and the bottom. Let's apply L'Hopital's rule again. By L'Hopital's rule, I'm going to differentiate the top. Derivative of e to the x is e to the x. Derivative of 2x is 2. And then I will apply the same limit. Notice that the denominator is constant now, right? Denominator is constant now, meaning that if I do direct substitution now, I will not be getting infinity over infinity form anymore. All right. Let's do that. Plug x equal to infinity. I get e to the infinity over 2. And this is infinity divided by 2, so infinity, right? You can always write this as d and e. There is a difference between these symbols, infinity, negative infinity, and d and e. But as far as this course is concerned, for us, infinity and d and e, they are the same. Negative infinity and d and e, they are the same as well. Okay, so I leave it up to you whether you want to use the symbol infinity or the wording does not exist. Both are acceptable form of the final answer. All right. Understand that we have to use L'Hopital's rule 2 times. First time when we used it, one copy of symbol was eliminated. We realized that one more copy of the symbol is there. We use L'Hopital's rule again to eliminate it. And then finally, after using L'Hopital's rule 2 times, we were able to compute the limit of this function as x approaches to infinity. Right? Let's repeat it here. All right, one more time. The same deal. I would plug x equal to infinity. Natural log of infinity square plus 7, that's log of infinity. It's clearly infinity over infinity form. Right, so if you plug x equal to infinity, immediately you get infinity in the bottom. In the top, you get log of infinity, which is also infinity. Right? So you can use L'Hopital's rule. Do the computation carefully. All right, all you have to do is find the derivative of the top expression, derivative of the bottom expression, apply the same limit on the ratio of these two derivatives, right? In order to find the derivative of the top expression, I must use the chain rule formulation of logarithmic function. This is what I am going to get. Limit x approaching to infinity, derivative of ln is 1 over inner layer, and then you multiply it by the derivative of the inner layer, which is 2x. Remember to create the full chain of the derivatives, right? If function has more than one layers. Derivative of 2x is just 2. All right, so this is the form that we get using L'Hopital's rule. Now, this form looks little tricky as there are two different denominators. This is a genuine denominator, so I would drop this down with 2. It's unusual to write something with two different denominators. So let's do the following. Send that x squared plus 7 in the bottom, and then we can cross out 2 from top and the bottom. Looks like we need to know the behavior of this function when x approaches to infinity. If you replace x by infinity, you get infinity in the top, infinity in the bottom. So this is still infinity over infinity form. Meaning I can use L'Hopital's rule one more time. Let's use it. Using L'Hopital's rule, we can say the following. Limit x approaches to infinity of this function is really the same as limit x approaches to infinity of individual ratio of derivatives of top and the bottom, right? Derivative of the top is 1, derivative of the bottom is 2x, right? Notice that the top is constant. This is no longer indeterminate form anymore, right? So all I have to do is plug x equal to infinity. Look, I am attempting to divide 1 by a huge quantity. When you divide any number by a huge quantity, the result will be closer and closer to 0. In case of denominator being symbol, you will hit 0. Again, remember, limit is the prediction only. All right, there is no way that we are going to reach at infinity because infinity is just a concept. It's not a number, right? So we are saying that when x is so huge, your function will be 0. That's how we interpret that first and last line. When x is so huge, our function will be so small, close to 0. Right? That's how we interpret that first line and the ending result. Now, I'm not saying that on the problem that I put on your exam, you will have to use L'Hopital's rule 2 times. It might happen that you may only have to use L'Hopital's rule once in some example. In the other example, you may have to use it twice. But this is the idea. As far as you have indeterminate form, you can apply L'Hopital's rule over and over. All right. Once that indeterminate form is gone, direct substitution should give you the answer, should give you the limit of the function. All right. Okay. Now let's move on and let's talk about continuity of the function. Remember, what do we mean by function being continuous? Well, the function is continuous if limit prediction matches with the exact value of the function at that particular input. All right, let's write down this statement in form of a mathematical statement. All right, so again, what I said is a function is continuous if limit prediction matches with the exact value of the function at the input A. This is what we mean by it. Limit x approaches to a f of x. Remember, this is the prediction only, where your function should go when x goes close to a. Right? If this prediction matches with the exact value of function at a, then your function is called continuous. Such function is also called connected function. Connected means the graph is connected. All right. Okay, so this is really the statement that tells you what do we mean by continuity. I would like to explain you this idea in terms of one graphical example. All right, so here is that example. Consider the following, the graph of a function f of x given below. Let's say I give you graph of some function. Let's say this is how the graph of a particular function look like. Suppose the function experiences a hole at particular input. It also experiences a jump at one more input. It experiences a vertical asymptote at a particular input. And let's say it experiences a sharp corner at one more particular input. All right. Let's try to first write down those inputs where we have this weird behavior for our function. All right. The part of the graph where function stays connected, they represent nice points. They represent continuous points. Function is continuous everywhere where the graph is connected, right? The only issue arises when the graph has, hole or jump or asymptotic behavior or sharp corners, right? Let's try to, label those bad inputs. All right, the first input is the input where the hole occurs, right? Let me label it as input B. All right. The second input is the input correspond to the jump, right? Let's label it as C. The third input which is interesting, is the one where function experiences vertical asymptote. Let's label it as D, right? And the fourth input is the one where the function experiences a sharp corner. Let's label that input as E, all right? Let me also put a few values on y coordinate, right? So these two values, the height at the whole end, that solid dot value, let's label it as K. This particular value, let's label it as L. And this particular value, let's label it as M. All right. Okay, I would like to answer a few questions regarding the continuity of the function. I'm going to create a small table with 4 columns. The first column will store the information about the input. All right, there are 4 inputs where I would like to investigate few things about my function. Input B, C, D, and E. All right. The first thing I would like to observe is what is the prediction of my function as x approaches to a, where my function should go when x is near B, when x is near C, D, and E. All right. I also would like to answer this question. What is the exact value of my function at this set of inputs? All right. And remember, continuity simply says that if prediction match with the exact value of the function, then your function is continuous. So last column will store this information. Is the function continuous? Obviously, we need to answer yes or no in that last column. Let's try to answer them. Okay. So let's work with the first one. I would like to know where my function should go when x is near B. All right, B is this input. Okay, how do we read the graph? What happened with my function as x goes closer and closer to B? You may notice that there are 2 ways that I can get close to B. I can go close to B from the right side of B, or I can go close to B from the left side of B. Let me remind you the rule of this game called limit of the function. You can go as close as you want without hitting that point, right? For example, if you try to observe the behavior of the given function when x is near 1, and you are approaching to 1 from the left side of 1. On the left side of 1, you have a number smaller than 1, right? You can consider x to be 0.999999999. This is a number very, very close to 1. You can consider that number, but you cannot consider 1, right? So you can go very close to 1 without hitting 1. That is the rule that we follow, all right? So I'm going close to B from the left side of B, very close to B. I just need to make a prediction where my function should go. So I'm going to see the left-sided graph of my function, the graph of the function that is to the left of B, and the graph suggests that, you know, my function is going to reach at K, right? So again, from the graph we can see there is a hole right there. But since it's a prediction and we are not going to hit B, prediction simply suggests that the function should go close to K. All right, if I approach to B from the left side of B. If I approach to B from the right side of B, then I need to look at the part of my graph which is on the right side of B, and I need to check what happened with my function as I go close to b? Looks like the function is going closer and closer to k value. All right, meaning that the left prediction, right prediction, they are exactly the same, right? If left and right prediction are the same, then limit exists and it is same as that predicted value. All right, so limit of your function near b exists and it is really k. Remember, we already dealt with this situation earlier when I showed you that fourth example, ratio of two polynomial. Remember, limit x approaching to 2, x square minus x minus 2 divided by x square minus 4. This is the indeterminate form that represent a hole or hole in the graph of the function at input 2, right? So graphically, it's very easy to compute the limit of the function. Remember the rule, you need to go close to b from the left and right. Without hitting b, you need to make a prediction where your function should go. Since I am not going to hit b, prediction says I can go closer and closer to k. The right side prediction says I can go as close as possible to k. Since both prediction are the same, limit is k. All right. What's the exact value of the function at b? Well, to get the exact value of the function at b, I'm going to look at the graph of the function at b. Looks like exactly at b, the graph experiences a hole, meaning the value of my function at b is unknown. It's undefined. So I would say undefined here. All right. Limit prediction and the exact value, they don't match. Function is not continuous. All right. Let's go to the next interesting input. The one where the function experiences a jump. What's the left prediction? Left prediction suggests that my function is going to take the value L. What's the right prediction suggest? Right prediction suggests that my function is going closer and closer to k. Left and right prediction gave me two different answers, meaning the limit does not exist. All right. What's the exact value of the function at c? Well, at c, looks like that solid dot represent the exact value of the function at c, and that is k. Since they don't match, function is not continuous. All right, graph is not connected. Let's check what happens at d. If I approach to d from the left side of d, looks like the function is going towards negative infinity. If I approach to d from the right side of d, function is going closer and closer to negative infinity. Left and right prediction, they both give me negative infinity. Limit of this function is negative infinity. Or just write d and e. As I said, for us, they both are the same. All right. What is the exact value of the function at d? Looks like none of this line are going to cross the y-axis, right? So value of my function at d is undefined. Function is not continuous. All right. Okay, let's check at e. If I approach to e from the right side, it tells me that my function is going to achieve value m. If I go close to e from the right side of e, my function is going closer and closer to m. Left and right prediction, they matches. Limit of this function should be m. All right. What's the exact value of the function at e? Looks like the exact value of the function at e is also m. Prediction matches with the exact value, function is continuous. Sharp corners are not that bad in terms of continuity. Graph stays connected. Even though it's a sharp corner, graph stays connected or continuity will be there. Okay, so these are the type of questions that you may want to keep in mind. There are other types of questions that also can be asked based on the graph of the function. Let me add few more sub problems here. Let's say we would like to know where my function is increasing. F is increasing on. I also would like to know where F is decreasing. All right, let's answer this question. Remember, these 4 points B, C, D, and E, it cut the domain, it cut the number line into 5 subintervals. All right, these are the 5 subintervals: negative infinity to B, B to C, C to D, D to E, and E to infinity. All right, these are the 5 points where my function changes its shape, right? So I would like to know where my function is increasing, where my function is decreasing. Recall what were we doing? You move from left to the right on each test interval and observe if graph is going up or going down. If graph is going up, then it's increasing function, positive slope, right? If graph is going down, function is decreasing. So reading graph is super duper easy. Doesn't even require any sort of calculus there, right? Let's check. If I move from left to the right on interval negative infinity to B, look, graph is going up, right? So on negative infinity to B, my function is increasing. All right. Let's see what happens as I move from B to C, from left to the right. Graph is still going up, so function is still increasing on B to infinity, sorry, B to C. All right, let's check the next segment, C to D. Move from left to the right. If you move from left to the right, graph of the function is going down. So on interval C to D, the function is decreasing. All right, on interval D to E, I move from left to the right, graph is going up, right? So on interval D to E, it is increasing. And then finally, on the last subinterval, E to infinity, move from left to the right, graph is going down. So E to infinity is the region where it is decreasing. All right. We can also ask this type of questions. F has relative maxima and find all relative minimum. Local maximum and local minimum. Remember, this is a maximum and minimum on a tiny, tiny region, right? Let's investigate that. First time we get the feeling that at C, function may experience the highest value. However, because of the open circle there, that is not the maximum value of the function at C. All right, there is a hole right there at that highest location that is not relative extrema. That's not even a candidate for relative extrema. The only candidate for relative maxima is this particular point, which is that sharp corner, the tip of that sharp corner. The relative maximum occurs at x equal to E, or in form of x comma y format, you can write it as E comma m, right? This is the relative maximum of the function. Do we have relative minimum in this graph? Right, we can check quickly. Looks like this end is going towards negative infinity. These two are going towards negative infinity. This is going towards negative infinity. Remember, relative extremas, they are the numbers. They are not the symbols. Being infinity, negative infinity, they can qualify as local minimum. So I would simply say that there is no local maximum or local minimum. Sorry, there is no relative minimum or local minimum for this particular function. All right. Once again, understand that all these questions can be answered by just reading the graph carefully. All right. And this is a perfect demonstration problem. It involves all type of bad inputs that we have experienced so far in this course. All right. Okay. So now let's move on and let's talk about basic differentiation formulas. Remember, there are 9 formulas in the list that we call basic differentiation formulas. We know if we know how to use them, we should be able to differentiate any function given to us. Let me mention here that any function can be seen in exactly one way out of 4 possible ways, right? Either function can be seen as a sum of different x power terms, or function can be seen in form of factors, or it can be seen in terms of layers, or it can be seen in terms of ratio. Depending on the initial form of the function, we are going to select particular differentiation rules. If function is in form of sum of various x power terms, we end up using the constant rule and power rule to differentiate it. If function is in form of factors, we end up using the product rule to differentiate it. If function is in form of ratio, we end up using the quotient rule. And if function is in form of layers, we end up using the chain rule to differentiate it. When we use L'Hopital's rule, I already show you we already have one problem where we use the chain rule, right? In that logarithmic numerator. Let's try to understand this concept. Now, before I go there, let me remind you that there are various set of wordings that we have used for derivatives. I mentioned that derivatives are really the most applicable things in all possible subjects, right? If you see a book written in geometry, right, they use the wording slope of the tangent line to represent the derivative. Slope of the tangent line is same as the derivative of the function, right? In physics, they use the wording instantaneous rate of change to represent the derivative of the function. In management, they use the word marginal cost, marginal profit, marginal loss. Whenever you see the word marginal, that marginal refers to the differentiation, right? So derivative has lots and lots of application in the real world. As I said, I really wanted you guys to recall that 3 ways to say the derivative. Derivative of the function, or slope of the tangent line at any given point, or instantaneous rate of change for the given function at any given point. All right. These 3 things, they are exactly the same, only the wordings are different. All right. Let's try. Keeping that in mind, I'm going to show you a set of examples that represent derivative of the function. Let's say find f prime x for each of the following function. Now for the first and second problem, I'm going to give you these 2 problems in 2 subparts, just to make sure that we understand the alternating set of wordings. I give you this function, something reasonably simple. Let's say 2x cubed minus 3x squared plus 2x plus 1. Find f prime x. That is the first question. Very easy to differentiate it, right? Look at that power rule, power rule, power rule, and constant rule. Derivative of 2x cubed is 6x squared. Derivative of 3x squared is 6x. Derivative of 2x is 2. And derivative of 1 is 0. All right. So that is the answer to the first question. If I ask you, compute the slope of the tangent line at x equal to 2. All right, all you have to do is plug x equal to 2 into the derivative of your function. Look, f prime at 2, 6 times 2 square minus 6 times 2 plus 2. This is 24 minus 12 plus 2, and that's going to be 14. The slope of the tangent line at x equal to 2, it's going to be 14 for this function, right? Let's try this one. Suppose I give you this function f of x equal to x cube plus 1 over x cube plus cube root of x minus 1 over cube root of x plus 3. This is the function given in form of 5 different terms. It should be clear that this is a variation of the first problem. All you have to do is rewrite your function in such a way that all x power term leaves in the numerator. So I am rewriting all the terms in such a way that all x power term leaves in the numerator. This example should look like the first one, right? It's an expression with 5 terms. All 5 terms, they can be seen in terms of power of x or the constant. We know how to differentiate it. Let's differentiate this carefully. Derivative of x cubed is 3x squared. Derivative of x to the negative 3 is negative 3x to the negative 4. One interesting thing that I want to point out here, every time you bring the negative exponent in the front, make a habit of writing it in the parenthesis. This is an origin of many sign errors, right? Those sign errors are very common if you don't use the parenthesis around that negative exponent. 1/3 x to the 1/3 minus 1. That minus 1, I want you to write it in form of common denominator over common denominator. Negative 1/3 x to the negative 1/3 minus 1. And then derivative of that constant 3 is going to be 0. Let me simplify this quickly. 3x to the 2 minus 3x to the negative 4 plus 1/3 x to the negative 2/3 plus 1/3 x to the negative 4/3, and then we have 0. Plus 0 is can be eliminated, right? Now let's say I ask you this second sub problem. Compute instantaneous rate of change at x equal to 1. Do not use the limit definition to compute instantaneous rate of change. Remember, instantaneous rate of change at x equal to 1 is same as evaluating the derivative at x equal to 1. Computation of the derivative or instantaneous rate of change for this function using limit definition is very, very tricky. All right, it involves some tedious computation. Do not use the limit definition here. It's literally one line work, and we really wanted to do that work in one line, right? Plug x equal to 1 in here, and you are done. 3 times 1 square minus 3 times 1 to the negative 4. Any power of 1, by the way, is going to be 1, right? 1 to the negative 2/3, and then 1/3, 1 to the negative 4/3. All right, let's carefully calculate this. 3 minus 3 plus 1/3 plus 1/3. This is 2 over 3. Slope of the tangent line is 2 over 3 at x equal to 1, or instantaneous rate of change at x equal to 1 is also 2 over 3, or derivative of the function at 1 is also 2 over 3. All right, so that's how we would like to interpret it. Here is the third example. It might happen that your function could be given in form of layers. All right, e to the power x square plus 5. How do you find its derivative? Well, pretty simple, no? Create the chain of the derivatives, starting from the most outer layer of your composite function. E is the outer layer, x squared plus 5 is the inner layer. Let's differentiate. Derivative of the outer layer, E, will be e to the inner layer itself, and then you multiply it by the derivative of the inner layer, which is 2x. Done. This is the derivative of the function viewable in form of the layers. We can create more fancy examples. If you remember, in your second exam, I created one example where you had three terms, and all three terms, they were terms with two layers. Here is an example similar to that. Let's say I give you this function f of x equal to natural log of x squared plus 5 plus e to the 3x squared plus 7 plus 2x plus 7 to the power 10. If I ask you to find the derivative of this function, understand that this function is constructed by adding three different terms. Each of these terms is in form of layers, right? I will have to use the chain rule to differentiate them. Let's do it carefully, all right? It's one line work, there is no trick. Create the chain of derivatives starting from the derivative of the most outer layer. Derivative of that ln will give you 1 over inner layer, and then you multiply it by the derivative of the inner layer. This is a complete chain representing derivative of ln x squared plus 5. Derivative of e to the 3x squared plus 7 is e to the 3x squared plus 7 times 6x. And then derivative of 2x plus 7 to the 10 is 10. 2x plus 7 to the 9 times 2. You do not have to simplify your final answer. However, each term needs to be in its simplest form, meaning if one term has two numbers, for example, here there are two numbers, 10 and 2. You need to multiply them. Here there are two numbers, 1 and 2x. So I would really multiply them out, right? So this is what we get as the derivative of the given function. All right. So remember, function can be visualized in exactly one way out of four possible ways. Either it can be seen in form of sum of different powers of x, or it can be seen in form of layers. If that's the case, you use the chain rule, right? Or it can be seen in form of factors or ratio. These are the two things that I would like to show you very quickly in terms of examples. So I'm going to, here is example number 4 that represents the function given in form of factors. Let's say I give you this function f of x equal to e to the 2x squared plus 3 times natural log of 4x squared plus 5. This is the function viewable in form of factors, something multiplied by something. Pretty easy to identify, right? You will have to use the product rule to differentiate this, right? This is the first factor, that's the second factor. Do the setup of the product rule. I'm going to leave the first factor as is, multiply it by the prime of the second factor. Then I will leave the second factor as is. I will multiply it by the prime of the first factor. Think about it, what it takes to get rid of those two prime notation. To answer that question, I need to ponder that what is the initial form of this function? Is it in form of sum of power of x? Is it in form of factors, ratio, or layers? Looks like this is a function in form of layers. I already know how to differentiate it, right? using the chain rule. Let's get rid of that prime notation. To get rid of this prime notation, I'll have to do the same thing, right? This is a function in form of two layers. I can use the chain rule to get rid of that prime notation. Let's do it. E to the 2x squared plus 3, derivative of that outer layer is 1 over 4x squared plus 5 times derivative of 4x squared plus 5, and that's going to be 8x. And then I have natural log of 4x squared plus 5. Derivative of e to the inner layer is e to the inner layer times derivative of the inner layer. Again, as I said, there is no need to simplify your final answer. This is good enough to be accepted as the final answer. All right, let's try the one example where function can be seen in form of ratio. Something divided by something, let's say natural, or let's say e to the 2x squared plus 3 divided by 3x squared plus 7. By now it should be clear that I am creating these examples randomly, right? The only thing I am keeping in my mind is 4 different ways to visualize the function. As far as those 4 ways are clear in your mind, you should be able to create your own example, and you should be able to, differentiate it too. Let's do that. This is a function in form of function in form of ratio. I need to use the quotient rule, right? Denominator times prime of the top minus top times prime of the bottom, and this is divided by the square of the denominator. Let's get rid of those prime notations. There are 2 prime notations here. This one requires you to use the chain rule. This one requires you to use the power rule and the constant rule. Let's do that. So as I said, I get 3x squared plus 7 times e to the 2x squared plus 3 times 4x minus e to the 2x squared plus 3 times 6x over that denominator square. And that's really the final answer that represents the derivative of the given function. All right, let's end this discussion with one example, representing one example indicating that log is the greatest simplifier in mathematics, right? Suppose I asked you to differentiate this function. Let's say we would like to find f prime x for this function, natural log of 3x squared 2x plus 3 to the 9 over e to the 7x times square root of 4x plus 9. All right, understand that if you choose not to use logarithmic rules, then the initial form of this function is in terms of layers. ln outer layer and inner layer is that messy ratio, right? You will differentiate the outer layer 1 over that ugly expression times derivative of that ratio. Now think about it, derivative of this ratio requires you to use the product rule 2 times, quotient rule once, and chain rules 10 to 12 times. This is a lot of work, right? And even after spending that much time, we will not be sure that our answer is correct or not. So what we do here is, we can take advantage of the logarithmic rules. In order to take that advantage, I want you to, rewrite the inner layer in such a way that all distinct factors are easily identifiable. In other words, if there is a fancy notation given in a factor of the inner layer, I'm going to write that fancy notation in form of a numerical power. I want you to count the number of distinct factors inside this complicated expression. How many distinct factors are there? Looks like 1, 2, 3 factors in the top, 1 and 2 factors in the bottom. Altogether, I have 5 distinct factors inside that complicated log, meaning I can break this log into exactly 5 pieces. The factors in the top appears with the positive sign, the one in the bottom appears with the negative sign. We have done series of examples like this in the class. Look, natural log of the first factor in the top, natural log of the second factor in the top, natural log of the third factor in the top. The remaining 2 factors are in the bottom, so they'll show up with the negative sign. By applying this rule, we manage to eliminate use of the product and quotient rule completely. Product and quotients are gone from the inner layer, right? We can now shift all the powers in the front to eliminate use of the chain rule 4 times. Since we are sending 4 powers in the front, we will be eliminating use of the chain rule 4 times. This is what we get if we shift the powers in the front. Now here, if you shift 7x in the front, that leaves us with log e. Remember, log e is 1. So I'm not going to write an additional step. Understand that once you shift 7x in the front, you get log e by itself, and log e is 1, so leftover will be really 7x. What we are saying is we have 2 different ways to write down that given function. Either you write your function in form of a single term logarithmic expression, or you write down the same function in form of 5-term expression. The difference is very clear. Computing derivative of this requires 10 to 12 minutes work. Computing derivatives of this requires less than 30 seconds. Let's do that. Final step, compute the derivative. This is a constant, 3 is a constant, natural log of 3 is constant too. Derivative of a constant is 0. Derivative of log x, it's 1 over x. Again, notice I am not touching the constant if it is multiplied with expression involving x. Derivative of log of the inner layer will be 1 over inner layer times derivative of the inner layer. Derivative of 7x is 7. Derivative of log of the inner layer is 1 over inner layer times derivative of the inner layer. No need to simplify your final answer, but be sure you simplify the numbers in each term. If there are 2 numbers in the particular term, at least you are expected to simplify. 9, 1 and 2, product will be 18, 2x plus 3. Here there is a cancellation of 2 in the top and the bottom. I end up getting 2 over 4x plus 9, and this is the derivative of the given function. Convince yourself that if I ask you to find slope of the tangent line for this function when x is equal to 1, all you have to do is plug x equal to 1 in here. Simplify numbers. If I ask you what is the instantaneous rate of change for this function when x is near 5, plug x equal to 5 in the derivative and simplify it, right?